So when it comes to things like disk, washer, / shell, I would say know your formulas. And will you see those things? So disk, washer, and shell are here. You might have to set it up. You might have to carry out the computation. The main thing is just know what things mean. It's not enough to be able to carry out computations. You have to carry out the right computations. So it's a matter of saying, okay, what do these things mean? So if we were to sketch a region, so let's say this is our region here, and we're just making up stuff. I don't know what's on the test. I'm an old person. I forget things very easily, except my problems. Oh, yes. I think you'll enjoy my problems. You'll come out of the test and say, well, some were good, some were okay, but Steve's problems, I enjoyed those.
How will we even know which problems will be until it's like after it's over?
If you don't know, then you haven't spent enough time with me. You know. You get a feel for it. So, all right, so let's suppose this is our region, and let's spin it. And let's suppose we spin it over here. Now, you don't have to make sound noises during the test, but okay. Let's suppose this is at x equals 6. And we'll give names here. This we'll say is y equals 1 minus x. And here we'll say y equals 1. Well, okay, y equals 2 minus x. Y equals 1 over x. But I'm not worried about things such as where do they intersect. I shouldn't worry about that, because actually these do intersect, but not in a very convenient way. Y equals, let's see, how about 3 minus x and 2 over x? I think that's better. 3 minus x and 2 over x, that feels better. I don't know if it is, but it feels better. It feels better. Okay, all right, so let's suppose this is our curve. All right, now, we're making things up as we go along. Where do these curves intersect? How do you find the intersections if they're not given to you?
Make them equal to each other, so this can...
Yeah, you'd set things equal. So be ready to find intersections. Now, hopefully, these actually have reasonable intersections. Otherwise, we're going to keep rewriting the problem until they do. So this becomes, what should you do here? Get rid of fractions, yeah. I don't like fractions. How do we get rid of fractions? Yeah, multiply everything by x. So 2 equals 3x minus x squared. X squared minus 3x plus 2 equals 0. So what does this do? Well, it turned out things will be relatively nice. And it factors. What does it factor as? Yeah, so x minus 1, x minus 2. Which says that there's a point 1 comma something, and there's a point 2 comma something. Well, when x equals 1, what should y equal? And how do you figure that out? Plug it into which one? Haha, trick question, either one. And you get 2. And if it's 2, you plug it in, you get 1. Wow. This is turning into a better problem than I thought. I should have put this on the test. No, you'll walk out of the test and you'll just think, oh, Steve's problem. was easy. Or will you? I don't know. We'll find out. Okay, so we're asking for volume. So volume of revolution.
When you said that, I just was like, no, it's not easy.
Since we're talking about things like disk, washer versus shell. Now, we can do it both ways. When you're after a volume of revolution, you can use, I'll just say washer for disk/washer. You can use washer or shell. Sometimes the problems will be very explicit, and they'll say you must use such a technique. So let's go ahead and just set up the formulas for both, since we're mostly about the setup. Let's talk about shell. Now, if I'm after the shell method, does that mean I integrate with respect to x or with respect to y? And the answer is, well, it depends. And you have to look at your scenario. I like to think about the question, okay, should I slice up into thin, tall rectangles or short, wide rectangles? In other words, vertical slices or horizontal slices. So there's two things that could happen. So we could have slices that look like that, or we could have slices that look like that. How do you know which kind of slice to take? Because ultimately that tells you what your setup should be. And if you take the wrong kind of slice, you'll end up setting up the wrong kind of equation. So, should we do vertical or horizontal slicing here? Vertical. Vertical is correct. Now, shell is just another way of saying cylinder. And the way you make the decision is think about what shape do you make when you spin that rectangle. So spin the rectangle. And you can just grab your pen and just say, okay, if I'm doing vertical slicing and I'm spinning around this line, what shape gets made? It's a cylinder. Now, if I do horizontal and I'm spinning around this line, what shape is getting made? It's a washer. So when in doubt, just slice it and spin it. You can use your pencil. We gave you a pencil. You are allowed to use pencils on this exam. If you're bold, you can use a pen. If you're really bold, like an extra large Sharpie, I don't recommend you to be bold. Please don't go with a Sharpie. But okay, so for shell, then we're going to do the vertical slice. And now we have to say, okay, we go to our formula. Which one is the shell one? The 2 pi one. So you have to make sure you're grabbing the right formula. So we have volume equals 2 pi, add up, a to b. Integration is just adding things up. Radius, height, width. And there's 3 things that correspond to measurements. And so that makes sense that we get a volume out. Now width is the freebie. So width, we're looking at our vertical rectangle. Width is the length of this rectangle. What is that in our case? It's the dx. It's how that part changes, so dx. All right. So that says we're an x integral, so we need to set up our x bounds. Where does x go from? X goes from 1 to 2. So 1 to 2. Okay, radius. What is the radius? Well, you have to go from your slice out to where you spin. So you have to remember, what does radius measure? It's a measurement of the radius to where you spin. So what goes into that? What is the radius in our scenario here? So this rectangle is like at an arbitrary x value. So I'm at an arbitrary x value in my vertical slice. I want to know how far away is it to x equals 6. What's the answer? Is it 6 minus x or is it x minus 6? I've heard a lot of people saying 6 minus 6, or is it x minus 6? Well, no, it's 6 minus x. Good. Why is it 6 minus x? And not x minus 6. Why 6 minus x? It's the large minus the small, right? 6 is to the right. It's the bigger value. If you had put x minus 6, what would end up with your answer? It'd be negative. You can't have negative volume. Even the AI knew, like, wait a second, you can't have negative area. And that's an AI. Okay, so be careful with your radius here. What's the height? So the height is the height of the rectangle. So you take the large minus small. So 3 minus x minus 2 over x. So put it all together, and you get 2 pi integral 1 to 2, 6 minus x times 3 minus x minus 2 over x dx, which you could carry out if you did some foiling and some little bit of computation afterwards, but in the interest of time, we won't do that. So now let's talk about the other method, which is our washer. Okay. So we're doing a horizontal slice by process of elimination. We've already done a vertical slice. So we're just, washer has the part with the big and the small radius. So we have volume equals pi, add up a to b, and then we have our big radius squared minus our little radius squared and times our width. Okay, so we're in this setting, that horizontal slice. All right, so the width is this little stretch here, that up and down portion. What is our width? dy. Yeah, so the width will either be dx or dy, it just depends. And we don't specify because we want it to be very flexible, because depending upon how you spin, things flip around. Okay, we're integrating with respect to y. Now the x bounds were from 1 to 2. Those were x bounds. You don't get to use the same bounds because we have to integrate with respect to y. So the x bounds went from x equals 1 to x equals 2. We are no longer using the x bounds. We're going to go to the y bounds. And so we're not going from 1 to 2. We're now going to go from 1 to 2. Good. But it's a different 1 and 2, right? It's the y equals 1 to the y equals 2. You knew it was very dramatic. I was building up to something. You cracked my very unsubtle code. Okay. All right. So we've got our bounds. We've got our width. Let's talk about our radius. So the little radius is the distance of the near part to where we're spinning, and the big radius is the distance to the far part. So if I think about my slice, it's the little radius is the closest distance to where I spin. Okay, and the big radius is the furthest to where I spin. Now, before we do anything else, before we write down the formula for radius, there's one other thing we have to do. What is it we have to do? Okay, so we need to figure out the radiuses. We need to change these to functions, x as functions y. But these were pretty simple functions. If y equals 2 over x, what is x? 2 over y. If y was 3 minus x, what is x? 3 minus y. So there's a certain amount of symmetry that comes into play. Okay, so radius. So the big radius. What is the big radius? Is it 2 over y? There's an awfully big gap there. Now, I could just have written that poorly, or perhaps there's something more than 2 over y. 6 minus 2 over y. Where does the 6 minus come from? Because it's the distance from this location to this location. Here x is 6, here x is 2 over y, and you need to take the difference. Okay, what's the little radius squared? Well, give you a hint, it's 6 minus something. 6 minus what? 6 minus 3 minus y. So, this becomes pi integral 1 to 2 of 6 minus 2 over y, quantity squared, minus, and this is 3 plus y squared. 6 minus 3 is 3, minus y plus y, dy. And there we go. We set up something with shell, we set up something with washer. Aha! And yeah, you should be ready. Ready to set up either one. So there's something. Blast from the past. Early on in our course. Well, let's see, we have a few more minutes, just a few. Anything else you want to, any last gasp? I see a hand up. Something with force? What kind of force? There's things with chains and there's things with pumping. Chain, okay. All right. So, if you're doing a chain problem, now I will say historically, people who have written chain problems on tests have done a bad job of writing chain problems. Because you have to know, there's a piece of information they've kept leaving out on recent exams, and I'm surprised that nobody has complained about it. But what do you need to know? Well, you have the ground level. We'll pretend like we're lifting something up. There's a pulley up here, and we're lifting up some object. So we know we're lifting up some object because it has the word object. All right, so here's our object. You basically have a few pieces of information. Now, the generic formula, and it's on the equation sheet, there's 2 places where work shows up. So this long equation, this is for when you're going to pump it up. You know, that's the pump kind of work. So if you have a tank and you're pumping, that's the long one. The short one, this is for when you're like lifting something up. So when you're lifting, you basically say the distance is always the dy. That's a freebie. So the hard part is the force. The force is the pounds. It's the weight. And by the way, on work problems, there's almost always one last sentence they put on the end of a work problem which says, include units in your final answer. What are the units of work? Because we are Americans, we say foot-pounds. That's right. You know, we're proud to live in America with our units that don't make sense. Okay, so we are foot-pounds people. All right, so don't forget, if it says include units, put foot-pounds. So work is you add up A to B, and then it says force, distance. The distance is, like I said, it's always a freebie. The A and B is where you start and stop. So put your work into force. I shouldn't say put your work into force. So force is the pounds part. And so what you do, you have to keep track of the chain. So you need to know where the chain is anchored. This is the part that they've left out on recent exams, but I will not let them leave it out right now. So if there's a work problem, you will know where that chain is anchored. I am not saying that there's a work problem like this. But if there is, you will know where the chain is anchored. So you need to keep track of the length of the chain, and there's a weight density of the chain. So let's say, oh, it weighs 2 pounds per foot or 3 pounds per foot. And so usually the chain part looks like some number minus the current level times the weight density. Sorry, I know we're out of time. This is the chain portion. And then plus the object portion. Now, the object may be constant weight. Maybe you're lifting a person out of the water onto the chopper. It could be a leaky bucket. A few years ago, they had SpongeBob SquarePants climbing up the Campanile in a heavy rainstorm. And because he's a sponge, he was absorbing water.
So did you write that one?
And no, I did not write that one. And so as a result, he got heavier as he went up. And so this is the weight of the object. And basically, that's what goes into the force portion.